Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about how many elements might you need in the mesh of a floating system when you're looking at hydrodynamics analysis in a tool like ProteusDS. Well, the answer is it kind of depends on the scenario, like everything in life. But let's look through a couple of examples to give you kind of an idea. So the first thing is, if you're just looking at sort of a typical floating, small scale floating system, this is a made up system. It's just a simple pontoon kind of system, on the order of sort of 10 meters, by 10 meters kind of thing. You don't really need a lot of panels in the overall mesh to get, a good representation of what's happening. So, behind the scenes, ProteusDS does split the mesh at the waterline to kind of add some extra smoothing in breaking up the hydrodynamics calculations involved. So you don't need to go too crazy with the amount of resolution, even though these are supposed to be kind of cylinders. But the main point is that you can get a lot with what looks like kind of a coarse mesh. The other thing is another common application is oceanographic buoys. So here we have a geometry mesh of a MOBS buoy. So it's about 3 meters diameter. MOBS buoys are used extensively in the scientific community. So there's a picture there. You can see it's got a bit of a sort of a chine on the bottom of the hull. Again, 3-meter diameter size there. Here's another great picture of one of these buoys being deployed. And I mean, this is in Rhino, taking advantage of the quad remesh functionality. So this is a step file, a surface geometry that we need to make a mesh from. So just hide the geometry. So this is with 200 panels just for this hull alone. And I mean, you've got tons of detail in there to handle, variations in the wetted area for buoyancy and drag and stuff like that. I really think it would be overkill to add too many more than that. And honestly, the kinds of things you're looking for is like a faithful representation of the geometry, right? And generally, of course, in terms of you don't have too much variation in sizes of the panels and as well in the mesh. But what about ship systems, like in, for example, the Shipmo 3D tool set? So we have some more examples to look at over here. Here we have the generic frigate. So this is a vessel that's about 100-ish meters long, 16-meter beam. And if you take a closer look at this as a sample project available that everyone can take a look at, in the output in panel hull, you'll see information on the number of panels. So this is in the half mesh, and this is the total, so 2,000. And it gets a lot of really great hydrodynamic response out of all this in the calculations. So this is a reasonably straightforward monohull as well. Something more complicated. We might look at an offshore supply vessel where there's sort of like more interesting geometry at the front with a bow, a bulbous bow here, and maybe a structure at the back for a bow thruster and just helping with the hydrodynamics of the propellers. You can see in this sample project also available that a little bit of optimization has been done to get a bit of a coarse mesh in here to just reduce the number of panels used overall. And when we go to panel hull and look at the number of panels in here, we see 1,700 in the half mesh, so the total is 3,500. Of course, you can get that's a simplification of more complicated systems as well. And if we look at a more realistic view of offshore supply vessels, they may have multiple bow thrusters and including one in the back as well, where you might want to sort of see what those gaps do to the hydrodynamics. And so, of course, you got to mesh those, and then the detail can add. Maybe you don't want to look at a simplified mesh in the mid region. Again, this is sort of like around 80 meters length, 16-meter beam or so. And if we look at the output here, oops, already got it open here. In total 7,700. So, there's nothing anything wrong with adding more detail. It's just that you'll have an impact on computational performance. It'll take longer to do the radiation diffraction calculations. It'll take longer to do the hydrodynamics calculations in ProteusDS and the time domain analysis as well. And yeah, and so, that's just giving you a few examples, but ultimately it all comes back to you in your application. If you're really worried about the number that you have, ultimately what you can do is change the number of panels you have that you're using and run a sensitivity analysis. So either increase it or decrease it, see what happens to the motion, is there a significant difference, and that sort of thing. So that's just kind of a really rough guide. When you're looking at smaller scale rigid body systems, maybe a couple hundred panels, and then ship systems that are fairly large, you might be looking at, a couple thousand. And of course, if you need to use more, right? But yeah, just wanted to give a few examples of in terms of the number of quantity of panels involved and what might make a sensible analysis. Thanks for watching.